that's fine. So just to remind you, we're talking about topological sectors of 3D n equal 4 superconformal field theories. And the theories that I want to study are 3D gauge theories with some gauge group G, and a hypermultiplet matter and some representation R. And the the field content of the vector multiplet consists of the vector field, some scalar, and two scalars. One of them transforming in the three-dimensional representation of SU2C, and the other one in the three-dimensional representation of SU2H. So these three-dimensional superconformal field theories, the superalgebra is always P4/4. It has as a subalgebra a conformal algebra and some R symmetry, which is SU2H times SU2C. The SU2 indices are A, B, and so on, and the SU2C indices are dotted. And the 1D operators that are topological, so the vector multiplet has this field content. The hypermultiplet has some scalars that I'm going to write as QA and QA tilde. And the 1D operators are constructed in flat space by starting with half BPS scalars that are of one of two types. There's Higgs branch operators, which have scaling dimension equal to JH and JC equals 0. And the Coulomb branch ones have scaling dimension equal to JC and JH equals 0. And we take one of these two. So in this case, I gave the example for the Higgs branch case, where all the indices are undotted. So we start with some operator. We put it on a line at some position x. Say the line is in the x3 direction. And then we contract it with some position-dependent polarizations. So in this case, UA is 1 if A is 1, and x over 2R if A is equal to 2. So we take O with all indices 1, and then O with some indices 1 and some indices equal to 2, multiplied by x over 2R to the power number of indices equal to 2, and that's the topological operator. So in this class of theories, for the Higgs branch sector, I gave the solution over here. So the idea was that instead of studying the theory in flat space, we study it on a sphere where the line becomes a circle. And then I can write down a partition function for just this 1D sector on the circle. And it's a Gaussian theory of two anti-periodic scalars, Q and Q tilde, that are constructed from this Q and Q tilde over here in the hypermultiplet fields.
Hello.
Hello.
Yeah, actually, we are not able to see the board very well. I'm not sure if it's a problem with ICTS or with DIFR. Is ICTS seeing it okay? Yes, sir. Yeah, because you are not being able to see the board from here very much.
Uh-oh.
I think ICTS is calling us, right?
Yeah. Hello?
Can you try once more, maybe? Yeah, now it's fine.
Now it's okay?
Yeah, now it's okay.
Okay.
All is from ICTS. So ICTS is there. Okay. Yeah, it's always that they have to call that in order for this three-way thing.
Yeah. Okay. So anyway, this was the review of what I did yesterday.
Yeah. It will auto-connect.
It will auto-connect? Okay. Okay, good. So let's see. I need an eraser. So today I was going to talk briefly about the Coulomb branch theory, and then I was going to talk about something else. So I'm going to put a sharp cutoff on the amount of time that I'm going to spend on the Coulomb branch case, half an hour at most, and then I'll talk about something else. Okay? What's that? so. Now I was gonna describe very briefly the 1D Coulomb branch sector and how one can solve that, and then I was gonna talk about the holographic duals of these 1D sectors. So I'm gonna put a sharp cutoff on the Coulomb branch discussion so that I get to talk about the other thing as well, okay? So the 1D Coulomb branch sector, so these are the 1D operators are built from 3D operators that have scaling dimension equal to JC. JC is the spin under SU2C, and they're invariant under JH. And we can construct, there are two such types of operators from which we can construct 1D operators. So the 1D operators are either constructed from these vector multiplet scalars, phi a dot b dot, which have dimension 1, and they transform as the spin 1 representation of SU2C. So this would be v a dot of x, v b dot of x, phi a dot b dot of 0, 0, x. And the other type of operators are monopole operators. So they have some monopole charge B, and they have this expression va dot 1 of x up to va 2jc dot of x, and then a monopole operator with all the indices a1 dot to a2jc dot at 0, 0, x.
I'm sorry, this is very remedial.
Yes.
But if I think in terms of the state operator map,
Yeah.
the monopoles are some flux,
Yeah.
and then presumably these things come from quantizing fermion zero modes.
Yes.
So somehow the only fermions that have zero modes are those that have the dotted indices?
No, the fermions that have zero modes are the fermions in the hypermultiplet which have dotted indices. I didn't write them down.
Okay.
Okay, so that shows that the value of JC is determined by the matter content.
It's like the Q has an A dot index. And then
Q has A dot. So these fermions are psi A dot and psi tilde A dot.
because Q acts with contracting
Yeah.
the A's and leaving.
That's right. And here these fermions have A dot.
Okay, excellent. And it makes sense because the size are charged fermions. That's why they have the zero.
Right. Okay, good. So I'm gonna, maybe I can erase this so that we can leave that over there and take a brief step back and say,
One quick
Yes.
question. The fact that the monopoles carry how many units of, just one unit of flux?
B.
B.
They're labeled by B.
And that C there, is that related to B?
No, this is, C is just an index that stands for SU2C, so I can put J here.
Okay.
C doesn't mean anything, yes.
And
Means Coulomb.
And what is J then? I mean, J is not determined itself.
JC is the spin under SU2C, so there's our symmetry SU2H and SU2C, and these operators have a transform under SU2C and the spin JC representation, and they have dimension equal to JC.
Yes, but what is JC?
I'll give the formula. Okay, so step back in 3D gauge theories. We can have local operators that are of two types. They can be gauge invariant polynomials in the fields that appear in the Lagrangian and derivatives. So we can construct operators that way. Or we can have monopole operators that are defined by requiring that they insert a certain number of flux units close to the insertion point. So the field strength, so when inserted at the origin, the gauge field close to the origin, sorry, F, close to the origin, should go like B over 2 times sine theta d theta d phi, the volume form on the two spheres surrounding the origin, with this coefficient b over 2. That's my normalization.
This is for the U1 theory. And
It also works in the non-abelian case.
then you specify the flux in each carton.
Correct. B is quantized. Yeah, that's right. You can specify the flux in each cartan. And this is quantized. B is quantized. The quantization condition is B dot the weights of the possible matter representation should be an integer. In the abelian case, if we could possibly add to the theory a hypermultiplet of charge 1, then B is an integer. Okay, so this is close to x equals 0. So these operators are defined by boundary conditions. We're specifying some boundary conditions for these fields. We can define many such operators to preserve supersymmetry. We also have this thing, if we just define it like this, it's not, in general, not going to be supersymmetric. To preserve supersymmetry, we have to supplement this condition by some singular behavior, so by some singularity in phi. As x goes to 0. So one can construct half BPS operators this way. I don't want to say, well, I don't want to go into too much detail, but I do want to say that the scaling dimension of these operators, the formula for the scaling dimension, or for JC, they're the same for the BPS monopoles, half BPS monopoles. It's just a sum over all the weights in the matter representation. W dot B, absolute value divided by 2, minus the sum over the roots, alpha dot B, absolute value divided by 2. So, yes.
I didn't quite understand this. To preserve SUSY
Yeah.
supplement, are you saying that the gauge field has a Dirac string and the phi B also should have some
The gauge field-
string-like thing? Or
Okay.
What did you say? What did you
Yeah, phi should go like 1 over x with the coefficient proportional to b. The fact that b is quantized means that the Dirac string is not observable.
Yes.
But yeah, usually we integrate over the smooth configurations of fields in the path integral.
Right.
If we want to insert the monopole operators, we say that we integrate only for those only over those fields for which the gauge field has this profile close to the insertion point.
Right.
If we want a supersymmetric monopole, we say, yeah, the gauge field should obey this condition, but the scalars in the vector multiplet should also blow up like 1 over x with a coefficient proportional to b. And that follows from the requiring that this configuration is supersymmetric.
You know, and one way to think of this is like, conformal theory is the state operator. This funny configuration in the path integral just becomes a normal flux configuration on the S2.
Right.
It's
The
very-
BPS condition relates this flux with phi.
Yes.
That is the reason that if you have some singularity in F, then that should be followed on phi.
That's right. Because you want to impose the condition that the variation of the fermions in the vector multiplet is 0, and the variation of the fermion involves f, and it also involves phi. Yeah.
And simply if this is too remedial, you tell me and we'll discuss it later, or you will indirect me to the right reference. But suppose we just had a U1 theory,
Yes.
okay, with a single field with just one charge.
Good. Great.
So delta would be basically Q times B, maybe by 2.
The q, if the charge is q. If the charge is 1, then it's just b times nf. If you have several.
Several flavors.
Okay, divide by 2. Yeah.
Now I was thinking that if you have a field B, then the monopole spherical harmonic starts with a certain J,
Yes.
which is roughly B.
Yes.
Is that the origin of this
Yeah.
formula?
Yeah.
Okay.
That's right.
And what was confusing me was that I thought you would have these fermions in that monopole spherical harmonic, and there would be 0 modes, and then you would have to quantize that to get
Yes.
the angular momentum. But J, So already the modes that you're quantizing look like they're in angular momentum J, the delta, and that quantizing also produces roughly the same. I
Sorry.
can just ask you later.
So okay. So yeah. Yeah. If you think about modes, you reach the same conclusion.
Okay.
Um,
Okay.
yeah.
Okay.
But these are scalar operators, right?
These are scalar operators. Yes.
These are scalar operators, but do they come from from because there were fermion zero modes?
Yes.
So when you quantize the fermion zero modes, you get scalar operators, and then there are also fermions. There's a super multiplet, right?
So Shiraz, you were saying about the
Yes.
J is related to B.
Yeah. Well, yeah. Okay.
So certainly, if you think about the modes, you can get this.
Yeah.
I need to remind myself exactly what the zero modes are in this case, but
Okay.
yeah. Right, but that's the right picture to have in mind.
Okay.
Yeah. Okay, good.
And I quantitated that
Yes.
the alpha dot B comes from the AG nodes. Quantizing. Where did that come from? The alpha dot B.
Yeah.
Okay. Roots. Roots.
The roots. So this is a contribution from the vector multiplet, and this is a contribution from the hypermultiplets to the dimension. Okay. So let me just tell you. Okay, unfortunately, we're not going to have a theory as nice as the one for the Higgs branch, the 1D theory, but we can still compute the correlation functions in this Coulomb branch theory. So I should just tell you what the steps are for deriving it and what the formulas look like, and then I'll give an example, and then we'll move on. Okay? So the procedure is the following. So several steps. The first step is place the theory on S3 with a topological sector on a circle parameterized by phi. So I'd like to draw a picture over here. So the picture is this. This is supposed to be a 3-sphere. And the big circle parameterized, so it's a 3-sphere. This is an S2 over here. And the circle is parameterized by phi. This is phi equals 0. Say phi equal pi over 2. Phi equal minus pi over 2. And phi equals plus minus pi. And we can insert these two operators in the 1D theory anywhere we want along the circle. And they're topological. Okay? Second step is doing supersymmetric localization on this configuration with these insertions is extremely complicated because you can't even solve for the field profile that's generated by these insertions. Okay, so the next step though is cut the sphere into two halves. HS3 plus and HS3 minus. So HS3 plus, the upper hemisphere and the lower hemisphere. Okay. And so far we didn't do anything. We just cut the sphere in our minds. But now we can imagine doing the path integral over the upper hemisphere and the path integral over the lower hemisphere. And we get, for each of them, we get functional of the boundary conditions. So we get like the wave function on this two-sphere. So if psi plus and minus are the wave functions on the two-sphere obtained by integrating out the theory on the upper hemisphere or on the lower hemisphere, then the partition function in the presence of these insertions, so partition function with insertions, is then just an integral over the boundary values of the fields. And then we have, so psi x boundary and we have psi plus of x boundary times psi minus of x boundary. I still didn't do anything. I just used cutting and gluing to write this formula. Of course, if we knew how to compute this, then we still have to do an infinite dimensional integral over here. Now, because the theory is topological, the 1D theory is topological, we can move all operators to the tips of the hemispheres. Okay, we can move them there. Abstractly, we can use the OP and replace them with just one operator over there and one operator over here. We can even just have no operators in the bottom hemisphere. We can put them all in the upper hemisphere. Okay? But then we should still have to compute, we still have to compute these quantities. However, in this case, one can argue that this path integral over here, over the boundary values of the fields, is a supersymmetric path integral in 2 dimensions on the 2-sphere, and preserves 2, 2 supersymmetry. Okay? So this, after we do that, this path integral, this theory over here, preserves 2, 2 supersymmetry in 2D. And what we can do is do localization on the boundary. So do localization on S2. So instead of integrating over all boundary values of the fields, we would get the same answer if we integrated only over more limited set of boundary values that are obtained after supersymmetric localization on the boundary. So
shouldn't there be a weight factor in the partition function? In the partition function, the weight factor, what is it given by e to the minus, means normally you have something.
In the partition function,
He's asking why isn't there e to the power minus s in z?
oh, because we just integrated, where, here?
Yeah.
We just integrated out, psi plus is obtained after integrating out e to the minus s in the upper hemisphere, and psi minus is obtained after integrating out e to the minus s in the lower hemisphere. And I actually didn't say what the boundary measure is, so whatever's left over, it can be included in dx boundary.
But you have to do an integration on S3 to get a state on S2.
Sorry?
You have to do an integration on S3 to get a state.
Yeah, on a hemisphere. That's right.
That is relatively.
Well, this is all conceptual, right? Like I'm not, I cannot do this. This is how it should work. I'll show you what I can do, but okay. So the idea is that this partition function then becomes okay. So instead of an infinite dimensional path integral after localization on the boundary, we have a sum and an integral. So it's the sum over b, integral over sigma. So this b is the magnetic flux through ds2. And this sigma is some constant value for one of the fields in the vector multiplet. It's the same sigma that appeared before. With some measure that one can obtain from 2D localization, and then we just have these wave functions evaluated now. They're only functions of 2 variables, sigma and b.
And b is fixed by the fluxes of the insertions?
Yeah, essentially, I want to think of it as a parameter here. So psi plus will be non-zero only when capital B is equal to the fluxes of the insertions. Yeah. Okay, good. And then next step. Next step is we can build. So we just still have to figure out. So this mu of sigma is given by the 2D localization formulas. I'm not going to write it down. It's the formula that some ratio of gamma functions. We still have to figure out what psi plus and psi minus are for whatever insertions we put in. So then the idea is we build, say, psi plus of sigma in B recursively. No, because I mean, all I'm doing is I'm taking this path integral and I'm just adding to it e to the minus t times the q exact term just on the boundary. So it doesn't care what happened away from the boundary. I thought this was a very neat idea due to one of my collaborators, Mikola. Okay, so we can build this wave function recursively, starting with the empty hemisphere, and then bringing in the topological operators one by one. Say from through the north pole of the S2. So let's say this is the north pole of the S2, this is the south pole of the S2. So suppose we focus on the top hemisphere, start with an empty hemisphere, and then you start bringing in one of the topological operators, you put it at the tip, and then you bring in another one, you put it at the tip, you bring in another one, you put it at the tip, and so on. And the effect of these operators that we're bringing in, they just act as some operator on these wave functions of sigma and b.
And how do you know all this? How do you know what bringing the operator does?
We can compute some things, which is we can have a monopole operator over here at the tip, and we can compute the determinant over the hemisphere. And we can also have a monopole operator over here, and in addition, some vector multiplet scalars inserted here, and we can still do this computation. So from that, we can extract what the action of bringing in operators is on this wave function of sigma and b.
Because it's topological, it's just once it's moved, you can put it on there.
That's right. That's right. That's right. So I'll give an explicit example. Before I give an explicit example, let me finish the steps. There's two more.
So the superstructure that you use for 2D localization is the same as the one that is used for this topological, to get the topological set.
Yes. Yeah. I mean, we can discuss how the 2D supersymmetry algebra is embedded in the 3D one, but maybe we can discuss that later. So then if phi 1 is bigger than phi 2 and so on, bigger than phi n, suppose all these angles are, we put all the operators in the upper hemisphere. Then the final formula is the expectation value of O1 of phi 1, On of phi n. This is 1 over the partition function, and then sum over b, integral over sigma, this measure. So suppose we start with an empty hemisphere. So the bottom hemisphere was empty. We didn't put any operators there. So we have psi 0 of sigma and b. This is just the wave function of the empty hemisphere. And then we have some operators, O1 hat through On hat, acting on the wave function of the empty hemisphere. I just have to tell you, sorry, okay, so one more thing. So to find psi 0 and the action of these O hats, we can do supersymmetric localization on the hemisphere. Okay, and let me just give you an example. So all I have to do in order to be able to compute is to say what the various ingredients are, what psi 0 is and what these O hats are, and that would be it. So we worked out all these formulas. Maybe I can erase this now. So an example, you want gauge theory with NF hypers of charge Q each.
It's like holography. You give me operators on the bulk, and you replace them effective operators only on the boundary. It's O1, yeah. Different boundary, but roughly like this.
Yeah, I guess. Right. So in this case, in this theory, the operators in 1D.
So if you
Yeah.
use the home branch operator,
Yeah.
the monopole one, but the local operator, that is the difference operator, or that's just multiplication?
Multiplication. Yeah, I'll say exactly what it is. So in this case, we have one of those. Is one scalar in the vector multiplet. And I just have to tell you how this acts on this wave function. So phi hat is 1 over r sigma plus ib over 2. Just multiplication by this quantity. And then for the monopole operator of charge b, so b is an integer, I just have to tell you what this m hat b is. And the formula is this. So minus 1 to the power qb, positive part of qb. Positive part means it's the number if the number is positive, or 0 otherwise, divided by r to the power qb over 2. There's a Polkammer symbol, 1/2 plus I r q phi hat qb plus everything raised to the power nf multiplied by some shift operator that sends sigma to sigma minus ib over 2 and b to capital B minus little b. Anyway, fairly complicated thing. So first act on psi of sigma and b with this shift operator, and then we multiply by this quantity. A fairly complicated thing, but we can work it out.
Wait, just to confirm. So I'm
Yes.
thinking of this psi like a Schrodinger wave function of a finite number of particles, right? Because its variables at fixed b are just sigmas, which is finite, right?
Yes.
This is so operator should be either multiplication by sigma or derivatives with sigma. Or,
Yeah, and this is what this is.
it's
Shift is e to the derivative.
yeah. So this is like non-relativistic quantum mechanics, and the analog of the L2 norm is this funny mu sigma norm.
Correct. Yes. Yeah.
Okay.
Yeah. I mean, I can write down the formulas for psi 0 and also for mu.
Sure.
But
And
yeah.
Hamiltonian is 0 because it's topological.
Right.
So, okay, so I give you the operators and yeah, fine.
Yeah. And so, for instance, just using these formulas over here that I wrote, you don't even need. So you would need the wave function if you wanted to compute expectation values. But for instance, even just knowing these operators without knowing the wave function, you can still compute OPEs. Because you can just compute the OPEs of these operators as they act on functions of sigma and b, and then you figure out what they are more abstractly. So for instance, you can check in this case that if phi is bigger than 0, then m minus 1 of phi, m1 of 0. So this is the monopole of charge minus 1 and the monopole of charge 1. So this is equal to product k equals 0 to q minus 1 minus I q phi of 0 plus 2k plus 1 over 2r, everything to the power nf. So here it is. There's an OPE of monopole operators that we're able to compute, which is the first example that I know where one can actually do something like this. With monopole operators, usually one just computes their quantum numbers. But in this case, we can actually compute correlation functions or OPEs. There's just a fun fact about this. As you take r to infinity, this formula becomes m minus 1, m1. So if you recall, in the r to infinity limit, we get the regular product. So this is like a star product. And in the r to infinity limit, we get the regular product of holomorphic functions on the Coulomb branch. So this is minus iq phi to the power qnf. So this is the equation that describes the Coulomb branch. Some number, some coordinate and some other coordinate is this coordinate to the power qnf. So this means that the Coulomb branch is C2 mod z, q, and f. This is the equation that describes that space. So you can figure out, from this you can figure out very easily whether, for instance, what the Coulomb branch is, what the relations between the various generators are, and so on. And there's a generalization to the non-abelian case where there are additional subtleties, but maybe we can, I can tell you afterwards what some of the subtleties are in the non-abelian case. Yeah. Psi 0 is, in this case, I can tell you what it is just a gamma function of 1/2 minus IQ sigma divided by square root of 2 pi, everything to the power NF. And it's supported on configurations where capital B is 0. That's what psi 0 is. And what mu does here in this case is that mu times psi 0 is just psi 0 conjugate.
So if I just do the psi 0 the S3 partition function,
Yeah.
I get couples in.
Yeah, that's right. So if you take one of these together and you multiply it by itself and you multiply it by mu, you find exactly 1/2 cosh of pi sigma to the power NF. That's exactly right.
The delta function is there because this a minus 1 and 1 is 0. The magnetic field is forced to be 0 because
Yeah, this is for an empty hemisphere. An empty hemisphere, it's got no insertions. Yeah, that's right. Yeah, and this formalism is not as nice as the other one, but one can still do computations and one can check 3D mirror symmetry, and we checked it in a few examples. It would be very nice to prove it in general.
And just to remind me,
Yeah.
last time the sigma dependence of the operators in yesterday's lecture was some tan h of sigma or something.
The sigma dependence of
For each insertion, you had some sigma dependence
in the Higgs branch case.
in the Higgs branch case, yes.
Yeah, that's right.
And you had some, and then you had to do some integral over sigma.
That's right.
So that could also be put in this language if you want, right?
Well, it's the same integral over sigma.
Yes.
You just have to do the sum over b, and then if you put the operator insertions, when you put this whole thing together, you can match this to the Higgs branch formula in the mirror dual theory.
Yeah, so the operator for the Higgs branch there was that tan h of sigma. Multiplication by tan h of sigma.
Well, yeah, it was slightly more complicated. It was some sine of phi 1 minus phi 2 plus tan h of sigma e to the minus sigma phi or something like
Yes.
that. Yeah,
But just a
that's
multiplicative operator.
it was just a multiplicative operator. That's correct. Yes.
sorry, so when you had free hemisphere, only B equal to 0 contributed. Depending on your insertions, like you can compute other correlators.
Yeah.
Psi 0 always has this B with 0, but then it has to change, right? Some other B's might contribute or not.
If you put all the insertions in the top hemisphere, then only B equals 0. Capital B equals 0 is going to contribute.
But otherwise, like some up, some down.
Yeah, that's right. The flux in from the top hemisphere should equal the flux minus the flux from the bottom hemisphere. So the total flux is total charge is 0.
And then these other factors, these cohorts will change this delta B, 0 to something.
That's right, because it shifts capital B.
Yeah.
This is where it does that.
I'm getting confused about something a little bit.
Okay.
Sorry. It's every time you have a multiplicative operator, some operator that's just a function of sigma, I would have thought those operators commuted with each other.
Yeah, that's correct.
But things, of course, they don't commute with the m's because there's a.
Yeah.
But in the Higgs branch, then why don't all the operators commute with each other?
The ones that commute would be the ones with integer spin. So these q's and q tildes were coming from 3D operators with half integer spin. That's the reason why they anti-commuted.
So they were not completely well defined in sigma.
Right.
I see.
With contractions description, right? So you had a bunch of orderings which would.
I was hoping to put that whole thing in this language. Once
Yeah.
you go into this language, it's just operators. And then the operators have to capture all the information.
Yeah, and that would be very interesting. I don't know how to do that. I mean, part of the difference, one important difference, I think, is that description is a redundant description because it has gauge symmetry. You're only supposed to consider gauge invariant combinations of q and q tilde.
Right.
Yeah, it would be very nice to put that in this language, and maybe one finds exactly the same. If one finds exactly the same theory, then that would be some sort of proof of mirror symmetry at the level of this 1D sector, which we currently don't have, and it would be very nice to have that. Okay. New topic. So, so far, I've explained that 3D n equal 4 superconformal field theories have some solvable 1D topological sectors, one with for the Higgs branch, one for the Coulomb branch. But as you might expect, there are some 3D n equal 4 superconformal field theories that have holographic duals. So the question is,
One question I have.
yes.
This is regarding the previous lecture also. So in these lectures, you were from R3 going to S3 and calculated the correlation function in the topological sector. So suppose we go to R2 plus S1, where this 1D, this dimension where you put in the operators, you take it to a circle and rest is R2. In that case, is the known, at least for the Higgs branch, the 2-point function, will it be just a inverse of sine of R over some period, this period of this circle? Means, is this known what the 2-point function will be in that case? For say QQT?
I'm not sure. I haven't thought about that background. You said R2 times S1, right?
Yeah. Means it's like you're taking only the
I
this
don't-
one divided.
I don't think that's conformally flat. So it may
Okay,
not be
okay.
possible to study the theory on that background, to study the topological theory on that background.
Okay. Thank you.
Okay, so the question is, what is the holographic dual? Do they have a 2D holographic dual? These are 1D sectors. So for that, first I should remind you, there are two types of ADS-CFT. There are dualities where we have supergravity in ADS. And that's dual to a CFT, superconformal field theory, with a matrix, large and limit, like the duality between supergravity on ADS 5 times S5 and n equal 4 superang mills at large n and large 12 coupling, or the duality between ADS 4 M theory on ADS 4 times S7 and ABJM theory. And these are, the theory is weakly coupled on the left and strongly coupled on the right. Okay. There's another class of ADS-CFT dualities which are between a higher spin theory in ADS and the ON or UN singlet sector of a large n vector model. And the main feature of these dualities is that the higher spin side is very complicated, and the CFT side is weakly coupled. So it's sort of the other way around. So the question is there something simpler? And studying the bulk duals of these topological theories might be something simpler, because the topological theories are solvable, as I explained, and maybe the bulk theory would be also solvable.
Do you expect to have a topological bulk, like a topological subsector of the bulk?
The topological thing is on the boundary.
But perhaps there's also a topological sector of the bulk that's due to.
Yeah, let's discuss what the bulk is. So first, let me discuss this in a bottom-up construction. So let's try to guess what the bulk dual should be, right? So in order to guess, we should recall two things from ADS-CFT dictionary. First is that a bulk field is dual to a single trace operator on the boundary. And the other thing we should recall is that a gauge symmetry in the bulk corresponds. So for instance, if we have a gauge field or the metric and so on, then we have a global symmetry in the boundary. So we have conserved current or the stress energy tensor and so on. So let's just do a bottom-up construction of the bulk duals, starting with the boundary theories. The boundary theory is topological. Topological theory has, in one dimension, has zero stress energy tensor. There's just one component of the stress energy tensor, and that component is zero, because the stress tensor must be traceless. So that means that there is no fluctuating metric in the bulk. Because if there were, it would correspond to a stress tensor and wouldn't be zero. So the bulk theory doesn't have a fluctuating metric. So what does the bulk theory then have? Well, we can try to guess based on what the boundary theory has. The boundary theory has a bunch of operators that are topological. So the boundary has operators JA of x such that the correlation functions don't depend on x. What that means is that these operators satisfy the fact that the derivative of these operators with respect to x is 0, up to contact terms. So of course, and that's the reason why the contact terms are the reason why the correlation functions can change if the ordering changes. What that means is that JA are conserved currents or just charges in 1D. So that means that the boundary theory has a global symmetry generated by JA.
Contact terms tell you the charges of one generator under the other.
Yeah, so from the contact terms, you would be able to get the structure constants. So let's just see how that, let me write the formula for that. So as I explained, in 1D, we can have either operators that are periodic or anti-periodic on the circle. Let me just talk about the periodic ones. I'm not going to talk about the anti-periodic ones. So restrict to periodic JA. And then the 1D OPE looks like this, JA of x, JB of 0. Well, we can normalize the operator so that the leading term is delta AB. And then we can get, so that the identity only appears here. And then we get the sum over the other operators in the theory. So I can write this. I can have one of two things, FABC, JC of 0, sine of x. So I can have either sine of something that appears with sine of x as x goes to 0, or something that doesn't appear with sine of x. So I'm going to call that DABC, JC of 0. There are only two possible structures that can appear. And the claim is that this FABC that you can read off from here, from the antisymmetric piece, are the structure constants of the symmetry. Okay?
So ABC is antisymmetric, DABC is symmetric.
Yeah.
And so far, A and B runs over all operators, single as well as multi-trace.
Yeah. That's right. Okay, so this OP, one can show that if you use the OP, you can show that if you transform all the currents like this, FABC, lambda B, FC, oh, sorry, JC, this is a symmetry of correlation functions.
It's the symmetry generated by JB.
Is the symmetry generated by JB, correct. Okay, so the structure constants for this global symmetry are FABC. Okay, so then what's the guess for what the bulk is? Bulk dual guess is the gauge theory. In a fixed metric, in a background, in a fixed background, and just fix it to be ADS or hyperbolic space, Euclidean ADS. In the spirit of ADS-CFT. And we should have, but because in the bulk we have one bulk field for every single trace operator on the boundary, in the bulk we should just have one generator of the bulk gauge algebra only for the single trace operators on the boundary. So for every single trace operator on the boundary. Okay?
This is a huge algebra. I mean, this is an infinite dimensional algebra because.
Let me give examples.
Okay.
It could be infinite dimensional on the boundary for sure. If I don't restrict to single trace operators, it's for sure infinite dimensional. But if I restrict to single trace to the well, let me just give examples.
But the single traces close among themselves and direct.
Yeah, I believe that's
Exactly, or just at large?
a large M, probably. My prescription is going to be just compute these FABCs from 3-point functions of single trace operators, and I'm going to declare that that's the bulk dual. So let's see if that could possibly work.
Does satisfy Jacobi identity trivially from just the definition?
Yeah.
So why doesn't DABC figure in this?
Sorry?
Why doesn't DABC appear in the transcription?
Well, FABC has to be antisymmetric. From DABC, well, DABC is extra information.
It's like the commutator generates
Yeah.
how one thinks chapter it transforms everything.
Yeah. But what do I think of this?
Yeah, so I think what happens, Shiraz, is that when you multiply two single trace operators
They're not, okay, got it.
at leading order, you get a double trace operator, but that's in the symmetric part.
Right. Right. But I was just wondering at subleading orders in 1 by n.
Subleading orders, I have no idea what happens.
Right.
It would be very interesting to figure that out.
It would be interesting because perhaps suggests an interesting deformation of the structure.
Yeah. Yeah,
So at large, it's just a
That's right.
universal enveloping algebra.
sorry?
Large and it will be universal enveloping algebra
Of,
the single trace algebra.
yeah, I don't want to, I guess that should be the total algebra, but yeah, I don't know if that's the correct gauge theory to consider in ADS.
At some point we'll have to explain to us what a universal is.
Multilateral.
All the words that you can build out of the
And
generators,
the products are what? How do you take
abstractly. Okay, so let's start with the 3D theory, SCFT. So first, let me do an example of the first kind of the second kind of ADS-CFT, where I have a large N vector model. So the simplest example of such thing with N equal 4 supersymmetry is N free hypers. Very simple. And there's the 4D dual of the UN singlet sector. There's supersymmetric higher spin theory. Oh, what happened over there?
ISP is left, so I'm disconnecting. Okay. Make it clearer for each other.
No, we also have better reception.
Okay. Okay. So, okay, so 3D SCFT and free hypers, 4D dual supersymmetric high spin theory. What is the 1D sector of the 3D SCFT? Well, it's just given by this theory. D phi q tilde I, d phi q I, where I goes from 1 to n. So for each hyper, we have a pair of q and q tilde. We have n hypers, so we have n such pairs. And this is the action. This is the whole 1D theory. What is the UN singlet sector? Because that's the thing for which we're supposed to be able to find a bulk dual. What operators are there? So this Q transforms in the fundamental of UN and Q tilde in the anti-fundamental. So in order to make singlets, we have to contract them. So J is Q tilde I QI. That's the operator in the UN singlet sector. Then we have J squared, then J cubed, and so on. In this case, I'd say only the first one is a single trace operator. The second one is double trace, then triple trace, and then so on.
So this is the analog of just one multiplet. You have just one multiplet, one UN multiplet of hypers.
Yes, that's right.
Of course, take NF UN multiplets of hypers.
Correct. Yes, absolutely. And then it would be more complicated.
Yes.
Right. In that case, I would have, if I had NF UN multiplets of hypers, I would have adjoint valued fields. That's right. That's right. So what is the bulk dual of this? In this case, it's just a abelian gauge theory in ADS. If we had NF multiplets of UN, it would be a non-abelian gauge theory in ADS with UN gauge group, UNF gauge group. Yeah. So in this case, in the bulk, there's the abelian gauge theory.
And you haven't said what the gauge action is in the bulk.
Okay. 1 over 4e squared into x squared to g f mu nu plus higher derivative terms plus boundary terms. On a fixed metric. So the metric is dr squared plus, I can take it to be this, sinh squared r d phi squared. That's the
Somehow
ADS
the fact
metric.
that Maxwell theory in 2 dimensions is empty is reflecting the topological nature of the bulk.
Yeah, so this theory is invariant under under area preserving diffeomorphisms,
Yeah. It has no propagating photons. It's not
and it also has no propagating photons. Yeah, yeah,
Even the
right.
non-abelian one is like that.
What's that?
Even the non-abelian one is also like that.
Yeah.
That's right. That's right. That's right. Okay, and I should say
There is no Einstein term, of course.
no, because there's no
Really
metric. Yeah.
So,
So I claim this is it. Okay, and I should say something about the boundary term here. The boundary term is needed for 2 things. One is sorry, you have a question.
It's probably stupid. But let me ask it.
Yes.
Because there are no propagating degrees of freedom.
Yeah.
Let's take the abelian case.
Yeah.
Because there are no propagating degrees of freedom, wouldn't it be that by field tree definitions you could remove all the higher error terms?
I don't think so.
I thought
I'm actually-
anything that vanished by equations of motion can be removed by field tree definitions. But since
Oh, is that right?
I thought so, but maybe not everything. Because, but you know, since there's nothing that you can write down that does not vanish, I thought you should be able to remove it.
Mm-hmm. Well, we didn't remove it.
Okay.
We didn't remove them. Okay, so boundary terms are needed for 2 things. One, making the action finite. In ADS CFT, we always need some boundary terms to do holographic normalization. And the other thing, which is slightly more subtle in this case, which is that if you solve the equation of motion for the gauge field, you find that it has a solution that grows with r. So the boundary is that r goes to infinity, and then a solution that's a constant, and then subleading solutions. And what we want is to identify this as the source for the boundary operator. So this is a situation of alternate quantization. So the boundary term must account for that as well.
1 over n the deformation corresponding.
1 over n. I don't know how it works beyond large n. Usually in ADS-CFT, 1 over n corrections correspond to loops.
Yeah, but so this is somehow higher derivative stuff.
Yeah, so there are, but okay, but let me first tell you what happens at leading order in n, and then we can discuss 1 over n corrections. Because in the boundary theory being so simple, we can actually compute. So in the boundary theory, so in this theory, star, we can compute all correlation functions of J, all endpoint functions of J, at leading order in n. Well, we can get the answer at all orders in n, but suppose we take the large n limit. And then we can ask, okay, what bulk action should we write down such that it reproduces classically, by classical computations in the bulk, it reproduces the large n limit of all these correlation functions. I can tell you what that action is, actually. So maybe I can write it over here. So those correlation functions, so of J, are reproduced by this following bulk action minus n over 4 pi d2x squared to g log of 4 cosine squared of pi f, where plus boundary terms.
Does boundary terms force you to do alternate?
They should, yeah, they should be designed in such a way that
But
you
you
should
decide
implement it.
to do alternate and then you decide, then you have boundary terms, or why alternate?
Because by analogy with higher dimensions, it's the constant mode of the gauge field that should be interpreted as the source for the current.
If you did the standard one, not the alternate one, then
Yeah.
something will go wrong.
Yeah, you wouldn't be able to reproduce the right structure of the correlation functions.
Then you'll be keeping the charges fixed, rather.
That's right.
It's not what you want.
Yeah. So anyway, so this end where f is epsilon mu nu, f mu nu. So in 2 dimensions from the field strength, you can make a scalar by contracting it with epsilon with the antisymmetric tensor. And I can write down an action like this. Well, this is the action that reproduces all these correlation functions in this case. You can expand it in f. The first term goes like f squared, and then there's an f to the 4th term, and then f to the 6th, and then so on. So in this case, we know all the higher derivative terms.
Amazing. It's like born and fed, meaning there are no derivatives of f.
There's no derivatives of f. That is true.
Maybe my statement should more accurately have been that you could remove those terms.
Okay. Good.
Equations of motion. In Yang, Maxwell equations actually are derivatives of f.
Derivative, yeah, that's right, that's right.
So maybe that's what I should really say.
But it, I mean, it could be. I'm not. It could well be that this can be rewritten as f squared. But then the relation between the ADS-CFT dictionary would be much more complicated for some reason.
No, but from what I was
Yes.
saying,
I
actually,
see.
it follows that the derivative.
The derivative. Okay, good.
F equals 0, constant is a solution.
Yes. Okay, good. Okay, so then maybe it makes sense that I didn't write terms with derivatives.
When you wrote down the OP, you had this FABC and DABC.
Yeah.
The DABC usually depends on the representation, right?
Yeah. Yeah, I don't know how to interpret the ABC in this case. I don't know what
But
representation of what group.
Yeah, the fact that you can compute the correlator and not just the commutator,
Yeah.
commutator correlators, that means you can reproduce the DABCs also, right?
Yeah.
So that somehow that is getting fixed.
So in this case, there's yeah, the claim is that this is the whole thing. Well, but in this case, there's just one operator, so there's no FABCs. There's no. It's just D111.
How does the ordering dependence come from this thing if you do ADS-CFT to this one? The ordering dependence also should come out.
So the on-shell action. So okay, maybe the abelian theory is too simple because there's no ordering dependence. Everything commutes. But in the non-abelian theory, you could write down something like. So actually, we did this thing, and it looks like in the if you have NF equal 2 UN multiplets, then you get the U2 gauge theory, and the action is the same thing with the trace here, and F is U2 valued. And in that case, the ordering dependence comes about in the following way. Because there are no propagating degrees of freedom, well, you're supposed to compute the on-shell action, right? And the on-shell action only depends on the holonomy of the gauge field. So there's some path-ordered exponential of e to the IA. And the ordering dependence just comes from the path ordering. So you can nicely reproduce the field theory formulas. The field theory will be in this way from the bulk.
So one probably stupid question. In the Higgs branch,
Yeah.
you had your boundary theory had a gauge. In one way of writing it, had a gauge field.
Sure.
Does that have anything to do with this gauge field? Probably not. Just to check.
Almost. If you didn't integrate over that gauge field on the boundary, then it would be a mass term.
Yes.
I think that mass term couples precisely to these currents, Q tilde Q.
Yes.
So that would mean that you're introducing a source for these currents. So that theory should also be described by the same thing, with different boundary conditions.
Okay.
So there is a relation. Okay. So second example. How much? Yeah.
I'm sorry. So you produced it for us by construction.
Yeah.
But the natural question is, in an example where you actually have ADS-CFT, can you check supersonet? Is there a sector of the bulk that looks like this? Or do you get it from the known bulk?
Yes. Yes. The answer is yes. I was going to do that.
Okay.
How much longer can I go?
Well, Gautam, I think, is going to have to go in.
Yeah, I have to teach,
Yes.
but you should carry on.
Yeah, complete the pressing things.
Well, okay. So what I have here is 2 pages.
That's okay. We'll Gautam. Yeah.
Okay. So
That's okay.
Yeah, absolutely.
the other example
Yeah, for
where I can answer this question at the end, on the second page, is the M2 brain example.
Oh, sorry, but even here in Vasilyev theory,
Yeah.
you could, in principle, try to address it.
Well, you'd have, you'd have to do localization in the bulk, but we don't even know, we don't know an action for the bulk theory. So, yeah, if that problem gets solved, then you can try to look at it. Yeah.
So Vasilyev theory, because this was UN gauge theory with some fundamental.
Yeah.
Right?
Free.
No, this is a free field theory, and the UN singlet sector is described by a supersymmetric version of Vasilyev theory.
If you want to gauge Vasilyev, you need to, the boundary, you need to gauge it with Chern-Simons, and that he explicitly does.
But here, the coupling constant doesn't really play any role, right? Or does it?
That is quite,
Yeah, of the 3D theory.
The coupling constant of the
It's
three.
free theory, right?
Yeah. Yeah, here there's no, yeah, the normalization of these Qs doesn't play any role, yes.
Yeah, so why is it Vasilyev? Instead of 3, it would be strongly coupled also.
It's quadratic. It's just free height.
Yes.
You have UN singlet sector, right?
UN singlet sector of a free hyper, the theory of free hypers. Right. What is the question?
Oh, okay. There is no gauge.
There's no gauge.
No, no. You're just restricting yourself to the UN singlet sector.
Okay.
At least that's my understanding of how these higher spin
Okay.
CFT dualities work.
It's the k goes to infinity limit of coupling it to Chern-Simons thing.
That's right.
Okay. But this calculation would have been also not very difficult if you had a gauge theory there, right? A UN gauge theory.
The Higgs branch, yes, your Higgs branch yesterday is asking.
Yeah, I mean, this action would be more complicated.
You just had an extra integral over sigma.
Yeah, that's right, yes.
The operator counting would go the same way.
Yes,
So you would just have gauge field in the bulk again.
yes,
This thing would be different maybe.
yes. But if maybe you wanted to have a SUN gauge theory, not a UN gauge theory, because if it's a UN gauge theory, then this operator Q tilde Q is one of the is
Yeah, then you have two.
set. Yeah, maybe. Well, okay.
You can UN singlets anyway.
Yes.
So maybe I'm missing.
Okay. I mean, this is an example. Let me talk about this. we can discuss this later. Okay. So in this case, we have this 3D CFT is ABGM theory at Chern-Simons level 1. As I said yesterday, we can't study the theories with Chern-Simons level, but there's a dual description, which is the UN gauge theory plus one fundamental hyper plus one adjoint hyper. And this theory has n=8 supersymmetry. So therefore, it has SO8 R symmetry. But the whole discussion so far was for n=4 superconformal field theories. So as an n=4 SCFT, this has SO4 R symmetry, which I was writing as SU2H times SU2C, as well as an SO4 flavor symmetry, whatever commutes with this SO4 inside SO8, which I'm going to write as SU2F times SU2F prime. So there's 4 SU2s that we have to keep track of. And the 1D theory, I can write down what it is.
This SO8 R symmetry is manifest in the Lagrangian of this theory?
No. Some of it comes from multiple operators.
Right, so SO7 is manifest?
No, I think it's just,
SO6?
I don't know what's manifest actually.
Without the hyper, that would be the content of the D2. This would be the D2 plane theory?
Yeah.
There SO7 is manifest.
Yes. I think the fundamental hyper actually breaks it. It might just be n=4,
Right.
and the rest comes from monopoles. Okay, so the 1D theory. Let me just keep only the adjoint hyper and then do the integral over the fundamental hyper. So then what I get is that I get an integral over sigma, which is now valued in the adjoint of UN. I have a determinant in the adjoint representation of 2 sinh pi sigma, and then a determinant in the fundamental representation, because I integrated out the hyper, 2 cosh pi sigma. And then I have a theory of these q's and q tildes that are associated with the hyper. So these are both adjoints of UN. And I have an action, e to the 4 pi r d phi trace q tilde d phi q plus sigma, the commutator between q tilde and q. This is what it comes down to. This is what the 1D theory is. This 1D theory has SU2F flavor symmetry. under which Q and Q tilde form a doublet. This is the same SU2F as this one. This one doesn't appear. All the operators in the 1D sector are singlets of this SU2F prime. So that means that the operators in this theory transform under SU2 flavor. So they have various spins under this SU2 flavor. If you look at try to build the operators, you'll find that if you look at the single trace operators, because these are the ones that we're interested in, there's one single trace operator for each spin of SU2F.
So usually Q tilde now does that under the R symmetry.
Yeah. Not Q and Q tilde. Q and Q tilde are these twisted fields.
Yeah.
So the R symmetry is gone.
One of the SU2 is gone.
Both. Both SU2H and SU2C. SU2C they were invariant under it, and SU2H was used for twisting. So SU2F and SU2F prime are the only ones that could have been left over, but I'm claiming that SU2F prime isn't. Okay, so the single trace operators are one operator OL for each SU2F spin L, and it starts at 1/2.
Highest weight of this is trace Q to the n.
That's correct. So it's trace Q to some power, Q tilde to some power, and the powers have to add up to L. Well, that's the schematic form. The ones with half integer L are antiperiodic. The ones with integer L are periodic. In this talk, we're only focusing on operators that are periodic. We could discuss the interperiodic ones also, but not now. So for even L, you can use this theory to actually compute the 2-point function.
And the operator in that trace is symmetrized, right?
With respect to what indices? SU2?
Yes.
Yeah, so, okay, you can write down, you can introduce some operator x, which is y1 q plus y2 q tilde. So instead of having q's and q tildes, I can package everything into some operator x with some auxiliary variable y. And then this operator OL of phi and y would just be trace of x to the L. And that's the entire formula. And then it's symmetrized automatically because the y's commute. Okay, so we can compute this, and we can compute OL1, OL2, OL3. So what you find is that this 2-point function goes like into the 3/2, and then the structure constants also go like into the 3/2. And we have formulas for them in our paper. They're just ratios of gamma functions. That's all they are. And then you can try to think, well, is there an algebra for which these are the structure constants? Because this should be the gauge algebra in the bulk. What kind of algebra is this? And we found that, so from this extract FABC, and then we noticed that these are same as the structure constants for the algebra of area preserving diffeomorphisms of a two-sphere. If you're familiar somehow with higher spin algebras, this is also HS of lambda with this parameter lambda taken to I, goes like I n to the 3/2, so it goes to I infinity. Anyway, the claim is that this is, there's some structure constants, then this is the algebra. So then in the bulk, claim is that there's a bulk dual is a gauge theory whose gauge algebra is infinite dimensional this time, and it's given by the algebra of area preserving diffeomorphisms of a two-sphere. So S in the bulk is 1/4 g n mil squared, d2x square root of g trace f mu nu plus higher order terms. In this case, it's very complicated because the algebra is infinite dimensional, so we couldn't go very far in the derivative expansion here. So I think we know this term, and then we know some combination of the quartic terms, but then we didn't go farther than that. So it's not like the higher spin case where we had the null orders in F expression. And by matching the correlation functions, the 2-point functions, we can get the 2-point functions and the 3-point functions. We found that 1 over g Yang Mills L squared is n to the 3/2 divided by 3 squared. So just by explicit matching. So this is the bottom-up approach.
And this L will be Kaluza-Klein modes on the S whatever.
Yeah, certainly. They should come from Kaluza-Klein modes on the S7, correct? There's a tower of half BPS multiplets. Each half BPS multiplet contributes one of these L's, one of these LLs. Okay. So now, Shiraz's question: is there a top-down approach to this?
So
Yeah.
the integrator of the fundamental, right?
Yeah.
If you were to keep it, then it adds some additional.
I think I can't construct. I think all the operators that I can construct from it are related to the operators that I can construct from the adjoint by the d-term relations. So I don't think I'm losing any information by integrating it out. Okay. Okay. Everything good? So, okay. Now, the 1D sector was obtained from the 3D theory by localization.
Yeah, sorry,
Yeah.
that had better have been because there's another description of this theory without any functionalities.
Yeah, that's right. So the 3D SCFT, from that we can get, maybe I can draw the arrows a little bigger, 1D sector using localization. So then you could ask, maybe if I take M theory on ADS4 times S7, then maybe one can do localization to get Yang-Mills on ADS2 with S diff S2 gauge algebra. I guess I would conjecture that. But obviously, I don't know how to do this computation. But I know how to do something, which is I can think about a sector of this, which is, well, it's related to the fact that this theory has SO8, the field theory that I'm not writing here, has SO8R symmetry. And from the n=4 point of view, it has an SO4 flavor symmetry. So that SO4 flavor symmetry should correspond in the bulk to some SO4 gauge theory with just n=4 supersymmetry. So a subsector of this theory is n=4 super Yang-Mills on ADS4 with gauge group SU2F times SU2F prime. And so this is like, we can study this theory maybe as a toy model for studying this localization computation. By the way, a similar computation was done by Rastelli and Bonetti and 1 dimension higher. So we can just do localization to get Yang-Mills on ADS2 with gauge algebra, just SU2F, because the 1D theory didn't have SU2F prime. This is a section of our paper. We did this. It works.
Is there information in the value of G-squared Yang-Mills then? I mean, that is, right? That produces the, oh, you got it. Yeah.
Yes, there is, yes. So you can reproduce this from this computation. So the way this works is that you get 1 over G 2D Yang-Mills squared L squared from this localization computation, this toy model localization computation. You get that this is pi divided by G of the 4D Yang-Mills theory squared L squared. And then if you look at the action of gauge supergravity, this is related to the Newton constant. So this is L squared over 4g Newton constant in 4 dimensions. And then by the ADS-CFT dictionary, this is n to the 3/2 divided by 3 square root 2. You might be wondering why it is that when we do this localization computation, we only get one of the 2 gauge groups and not the other one. Like, what's the difference between them? The difference between them is that n equal 4 super Yang-Mills has 6 scalars, but on ADS4, these 6 scalars transform, 3 of them transform as a triplet of SU2H, and 3 of them transform as a triplet of SU2C. Now, these scalars have masses in ADS, and they should correspond to operators of dimension 1 or dimension 2. And the correspondence is different for these 2 gauge groups, SU2F and SU2F prime. And that's needed in order to preserve supersymmetry.
So this thing here is just, is this right, that if you take the gauge supergravity, the
Yeah,
ADS4 gauge supergravity,
yeah,
that has an SO8 gauge field.
correct.
You just restrict that SO8 to SO4 and just look at it in an ADS2 subslice of ADS4, and that's what this is?
ADS4 sub, first I restrict to an
First
SO4.
you restrict to SO4, but
Yeah.
just to get this final thing, then you also restrict to an ADS2 slice.
Well, you have to do this localization procedure. And what happens is that you find that the fields are independent of one of the coordinates in ADS4. And then you find some action on, as far as I remember, I think it was like a half an ADS3. But that action is a total derivative. And the boundary of that half ADS3 is an ADS2. And that's how you get the gauge theory on the boundary.
But
So effectively yes, but it's slightly more involved. You pass through an ADS3 where you have a total derivative action.
Yeah, what I was not saying is how you get the, I mean, from my point of view, how you get the value of this G squared Yang. You know,
In what approach?
in the nihilist way of
Yes.
thinking of it. I was thinking of it something like a dimensional reduction.
Uh-huh.
If
Oh.
you, that would, this G squared Yang-Mills has dimensions, right?
Yeah.
Normally that comes from the volume of the box. And you're getting the volume of the box, but with some particular pi's and so on.
Yeah.
That, I wouldn't know how to use. So it sounds interesting.
Yeah. That comes from the localization computation. I don't think I have a more conceptual.
Right.
What was this step that I missed? Everything on ADS4 that this one was localized to n equals 4 super Yang-Mills on ADS4?
No, n equal 4 super Yang-Mills on ADS4 is a subsector of that.
Oh, okay.
That's all.
Just part of gauge supergravity.
Part of, yeah, it's even, it's a subsector even of something smaller than this, which is the consistent truncation, which is gauge supergravity and ADS4, without the Kaluza-Klein, the higher Kaluza-Klein modes. Yeah, and this Yang-Mills theory with gauge algebra SU2, this is of course part of the bigger algebra.
So
This is
the full
part of that.
diffeomorphisms, in order to get those, you would have to have gravity probably.
You have to have the higher Kaluza-Klein mode, yeah. And yeah, I'm not sure to what extent gravity is important or not. The gravity, the higher Kaluza-Klein modes are the ones that contribute these extra operators. But of course, in order to, I mean, this is just, I just ignored the gravity part. I didn't do localization for that part. Of course, in order to actually prove it, you'd have to do it.
But this bigger gauge group is not coming from gravity, it's coming from
The bigger gauge group comes from the,
But high Kaluza-Klein modes are high Kaluza-Klein modes of gravitons.
everything's with maximal supersymmetry, everything's related to gravitons. If I think about it only from the n equal 4 point of view, then they are not related to gravitons. But n equal 8 does relate them. Okay, so the summary is that 3D n equal 4 superconformal field theories have topological sectors. I showed you how to solve them. 4 gauge theories with charge hypers. And there are some explicit descriptions for Higgs branch and Coulomb branch. And at large n, bulk dual of a topological sector is just a gauge theory in ADS2. That's our proposal. We only checked it at leading order in n. It would be nice to see how it works at subleading orders.
And just to, as the conceptual difficulty of just taking 11-dimensional supergravity on ADS 4 times S7 and trying to do the localization there is that you don't have an, what is the conceptual difficulty of that? Is there no off-shell formalism that preserves the right amount of supersymmetry?
Yeah, but you only need to preserve one supercharge, so it's not, yeah, I don't know what the conceptual difficulty is. It seems very complicated.
It seems very complicated,
Yeah.
but there's a clear starting point.
Yeah, there's starting point. Yeah, I guess so.
You seem very pessimistic.
Well, I don't know if it's fully understood what the integration measure is, for instance. Like you need to answer these questions. The classical action is not enough. Like you have to have a quantum definition of the theory.
I see. Yeah, maybe you get all the details right, but just to see that you're getting gauge fields with this, that the localization manifold is the right thing.
Yeah, I agree with that. Yeah, for that it might, you might just, maybe it's enough to just look at these Kaluza-Klein harmonics and do some truncation on them, like this one, where instead of looking at the lowest codes, the whole gauge supergravity, I just looked at some subsector of it. Maybe if you look at the higher KK modes, you just look at some subsector of those, and then you see that it localizes, and then you get this theory. Maybe something like that can be
I
done.
was just wondering whether it might be
Yeah.
easier to look at the full 11 dimensions.
Full 11 dimensions.
Find PS2 maybe.
Find ES2. Yeah. Yeah. Maybe. Yeah. Maybe. Yeah. Okay. Yeah. I'm sorry for going so much over time.
No, thank you for it.
Yeah.
Any questions? Richard?
Questions? No, we are fine.
Could you hear today, Ashok?
Yeah. In the middle it broke for a while, but then we could manage. I mean, now we are directly connected to the alpha. It is okay.
Okay.
So when ICTS is not connected, is it considerably better?
Yeah, certainly today it was considerably better.
I wonder if we could do 2 calls. Let's see.
Two
Yeah,
different
probably
connections.
technical people will have to figure out
Yeah.
the best way to do this.
Okay, how about here? Any questions?
Thanks a lot.
Yeah.
So one comment. So this infinite dimensional nature of the gauge algebra is coming from the fact that you are adjoint, right? If you had fundamentals, then it would be a similar story, and getting the gauge group would be the global symmetry. Right? So at least in the finite dimensional case, I suspect the multitraces essentially form letters and give you this enveloping algebra type of structure, and then the finite n would be some deformation of that structure. And I think mathematicians have studied
Mhm,
possible
mhm, mhm.
deformations, quantum, I think they call it quantum deformations, something like that.
Mm-hmm.
So that could be a candidate that could match with finite deformations of the structure.
Mm-hmm.
It works in finite dimensional cases, presumably similar structure.
Okay, I have one sort of half-related comment, which is, I mean, of course, this really goes off your line of attack, but which is this way. Suppose you took UN times UN theories.
Yes.
Okay. If M is small, you can sort of forget about them being gauged.
Yes.
Okay. So you could, and then this becomes like a flavor symmetry.
Yes.
Okay, and so it's like a fundamental theory.
Yes.
But if M is the same size as N,
Yeah.
it's like ABJM.
Yeah.
It's like an adjoint.
Yeah.
So it's along the lines of what Abhijit was saying, that the full infinite dimensional symmetry that you're seeing when you have adjoints
Yeah.
came from the multitrace sectors of the fundamental viewpoint.
Mm-hmm. 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 Oh, I see what you mean. Yeah, that would be very interesting to see how that works. Yeah, if one could do something like that. Yeah.
So something that looks
Yeah.
like just like a weak 1/n deformation of a simple gauge structure.
Yeah.
When n becomes order n, it should give you this whole shebang.
Yeah, that's right. That's right. That's right. Yeah, it would be very nice to study that case.